Okay, so here we go. This is the gas variables POGO worksheet that we're working on. Working in groups, going stop sign by stop sign, and we should be up to the first one where you got stamped yesterday. And so we're going to go over, we're going to discuss these questions and see if we agree on the answers that we have for them. So I'm going to be calling on people at random to share their group's answer. So we are starting with number 1 in Model 1. What does a dot represent? And this is going to be G. Graves. What do you guys say? Particles? Okay, we all agree with particles for number 1? Can we be more specific in the case of this worksheet? Gas particles? All right. Jaden, what did you guys say for number 2? Okay, name 2 materials that the containers in Model 1 could be made from that would ensure that they were non-flexible. And they said glass and metal. Do you guys all agree with that? Would that work? Okay. Does anybody want to share out another one maybe? Do we have other ones? Anybody want to volunteer their answer that might not be up there? Mylar, and we do have glass. But Mylar, that would be those like shiny balloons that look metal. And plastic, all right. So we only had to list 2, but there's 4 choices up there that would work. Did you guys come up with any others that I didn't mention there? So you guys got to understand that the non-flexible and flexible flexible would be like balloons that can get larger or smaller depending on the internal pressure or how the particles are moving inside. These would make non-flexible containers. Non-flexible containers meaning they're going to always stay the same size. So if non-flexible containers always stay the same size, what always stays constant with the gases if you use a non-flexible container? Can anybody answer that one? Okay, what variable will always stay constant if you use a non-flexible container? So different variables we have: internal pressure, external pressure, amount of gas, volume, temperature. If you have a non-flexible container, what will not change? Huh? The container's volume. Very good, Josh. Thank you. All right. So, and that's kind of leading us into what we're talking about today on the next part, where we go into flexible containers so the volume can change. All right, number 3, in Model 1, the length of the arrows represents the average kinetic energy of the molecules in the sample. Which gas variable, internal pressure, volume, temperature, or amount of gas, is most closely related to the length of the arrows in Model 1? So what did you guys put down? Kayla. Where's Kayla? I know you weren't here yesterday, but do you know what your group put for this or no? Can somebody in your group answer then for you? Temperature. You guys all agree with temperature? Okay, so why is that? What is average kinetic energy? The length of the arrows. What does that really mean? What's that mean in basic terms? If an arrow is longer, what does that mean about the particle? It's moving faster. And isn't that really what the average kinetic energy is? How fast the particles are moving? So it makes sense that that would be most closely related to temperature. Okay. All right, the table for number 4. All right, complete the following table for the 2 experiments in Model 1. So for experiment A, what was the independent variable? Remember that the independent variable is another name for manipulated variable. So the independent variable is the thing that we're changing on purpose. So do we have an answer for that, Teresa? So what is the independent variable in experiment A? Internal pressure. Do you guys agree with that? The independent variable for experiment A? What do you guys think, Bailey? You think yes? Internal pressure is the independent variable for experiment A. Does anybody disagree? Nobody disagrees? Okay, then I guess you guys all got that wrong. Oh, Jade, you disagree? Thanks for raising your hand the first time. The amount of gas, why would we say that? Oh, hey, look at this. I just read the title of this Model 1, Experiment A. It says Model 1 is gases in a non-flexible container, and Experiment A says adding more gas. So that's what we're doing, is adding more gas. So that's what we're changing on purpose. That's a manipulated variable, aka independent variable. So that means that we would put amount of gas for that. Yes, did everybody get that? Because if really that many people disagreed, you need to change that and you need to understand why. Okay, the independent variable is the manipulated variable, first of all. I know that's a different term than what we usually use, but the thing that we're changing on purpose. And in this first experiment, we're seeing what happens if we take a container that cannot expand or shrink, it's non-flexible, and we add more gas to it. Okay, so let's stay with experiment A going down in this column. And what would the dependent variable be then? Pressure. Which pressure? Pressure external or pressure internal? Outside pressure or inside pressure? Inside pressure would be our dependent variable. If I look at these different variables, I can see, of course, as expected, that the volume is not changing, which is good because it's a non-flexible container. The external pressure, so the pressure from the outside, is not changing either. We're keeping it in the same environment. But what is changing is internal pressure. Okay? So I would say internal pressure would be our dependent variable. What are our controlled variables or constants? What's staying the same in this, Jerry? The container. So the type of container, type of gas, amount of gas. Amount of gas would be a constant. Well, we were actually changing the amount of gas, right? So that wouldn't be a constant. Oh. All right. What about out of these ones? So which one stayed the same? What was that? Okay, so the volume didn't change, so we could also write volume. The external pressure didn't change, so we could put pressure external, did not change. The other thing that did not change is temperature, so we could put all those things, okay? So experiment A, we added more gas to the container, and the pressure went up inside. Does that make sense? If you had a container that could not expand, and we added more gas, it would make more pressure inside. Does that make sense to you, common sense-wise? Should, right? Okay. So next is experiment B. So what did we change on purpose in experiment B? The temperature, right? Thank you, Josh. So our manipulated or independent variable here would be temperature because we are heating the gas. So we're increasing the temperature on purpose. So that's this one. Temperature is going up. We're doing that on purpose to see what happens. Again, a non-flexible container. So if we look at the other variables, we see the volume doesn't change, the external pressure doesn't change, but what does change again here is the internal pressure. Okay? So internal pressure would be our dependent variable. Got that? The things that stay the same, you could say container and type of gas again, but we could also say volume stays the same. We could say external pressure stays the same. We can't say internal pressure because that changes. We can't say temperature either because we changed the temperature. What we can say, though, that we don't see listed here is remember that lowercase n, which stands for a number or quantity, talking about amount of gas, because in each picture there are 4 particles here, 4 particles here, 4 particles here, so we are not changing the amount of gas. Does that make sense? So out of all of these, we really have like 5 variables we're looking at. We're looking at volume, we're looking at pressure internal, pressure external, temperature, and amount of gas. Okay, number 5, of the variables that were controlled in both experiment A and experiment B in model 1, one requires a non-flexible container. So non-flexible container is needed to keep what constant? You said it earlier, Josh. Non-flexible container is important to keep what constant? Volume. Because if we have a non-flexible container, the size won't change. It won't expand and get larger. It won't shrink and get smaller. Okay, read this. Pressure is caused by molecules hitting the side of a container of other objects or other objects. Okay, that's your definition for pressure right there. Pressure is caused by molecules hitting the sides of a container or other objects. The pressure changes when the molecules change how often or how hard they hit. A non-flexible container is needed if the gas sample is going to have an internal pressure that is different from the external pressure. I repeat, this is important for today. You still here, Avion? A non-flexible container is needed if the gas sample is going to have an inside pressure that is different from the outside pressure. If a flexible container is used, the internal pressure, the inside pressure, and external pressure will always be the same. And that's going to help you today. If a flexible container is used, the internal and external pressure will always be the same because they're both pushing on the sides of the container equally. If either the internal or external pressure changes, the flexible container walls will adjust in size until the pressures are equal again. And that's going to be our main idea for what we're doing next. Okay, so try to move a little more quickly here. Name 2 factors related to particle movement that influence the pressure of a gas. We've got Avion. What'd you guys put for that for number 6? 2 factors related to particle movement that influence the pressure of a gas. What do you guys say here? You had an answer down, right? Kyle? Internal and external. Internal and external what? Pressure? Is that name 2 factors related to particle movement? And well, we're trying to see what influences that pressure. Jerry, something to add? Temperature and volume you put? How do you guys feel about that? Well, temperature would influence the speed of the particles, which would then influence the pressure. Which the speed of the particles, remember, is average kinetic energy. So I could see that. Volume also, if we have a smaller space, say, the particles are going to bump into each other more often. They're going to bump into the walls of the container more often. All right. Number 7, provide a particle level explanation for the increase in pressure observed among the flasks of experiment A. So why did the flasks that were sealed, why did the pressure go up in experiment A? Why does that make sense on a particle level? Giovanni Clark. What did you guys put for number 7? What is it? More particles. So in 7, we did have more particles. We were adding more particles. And so what does that mean? What are they going to do? They're going to try to spread out, right? But it's a non-flexible container, so they can't really. Let's put it this way. If we were gas particles in this room, and there were just this many gas particles for each one of us, how often would we bump into each other if we were trying to walk around? Maybe a little bit. Would we be forced to like bump into the walls? No. What if we took 1,000 more people and added them to this room? What's the chances that we bump into each other and therefore bump into walls as well more often? Okay? So when we're adding more particles, there's going to be less space. There's going to be more collisions between particles. And there's going to be more collisions with the sides of the container. All right? So that's the main idea. More particles, more collisions. Okay, number 8, what'd you guys put for that, Kanye? Provide a molecular level explanation for the increase in pressure observed among the flasks in experiment B. Okay, so that was the one where we increased the temperature, we added heat. So what does that make the particles do? Makes them hit the wall faster with more force. Okay. So add heat, particles faster. And ultimately, again, this is going to mean more collisions more frequently, right? So if the particles are moving faster, they're going to hit the sides of the container more often and with more force. Okay. Number 9, predict what would happen to the volume and internal pressure in experiment A of model 1 if a flexible container were used. Anybody want to volunteer that one? Alyssa, what did you guys put for number 9? The pressure would decrease. Internal pressure would increase. So we're saying we've got a flexible container and we're putting in more gas. The internal pressure would increase. So I'm going to say pressure, lowercase I, pressure internal, increase. And the external pressure would increase. So let's say this is a balloon we're talking about, and we're adding more gas to it. What is the pressure on the outside? Is there a way to explain the pressure on the outside? Jade? Can you wait just a few more minutes? What is the pressure on the outside? Didn't we have a term for that in our notes? Meteorologists use it for weather. The pressure that's on us all the time. Atmospheric pressure. So just because we blow air into a balloon, would that change the atmospheric pressure? No, that's going to stay the same, right? What happens to a balloon in terms of volume when we blow it up? It gets bigger, right? That's the whole point. We blow up a balloon, it gets bigger. Brynice, if that gets bigger, then what is that? What variable is that we're talking about? Size. What if the balloon gets bigger? What variable is that we're talking about? The size. It's expansion, but what is that variable talk? What variable measures size or space? Kyle? Nope. Good try. Volume. Yes, volume. Okay, so if we add more gas to a flexible container, the volume is going to increase. So I'll put V up arrow, volume increase. Now, let's look back at what Jerry said the first time. The internal pressure. Would the internal pressure actually increase? Okay, so here's the main idea. Really big point. The internal pressure and external pressure in a flexible container will always be the same. So what's changing as a result? So I'm going to do this. Now, here's the thing, though. When you initially blow the air in there, there's going to be more pressure on the inside than outside, sure. And that's going to make the walls of the container, or the balloon, say, if we're talking about that, move outward. But they will only move outward to a point, the volume will increase to a point where the internal pressure equals atmospheric. And then it'll stop. Okay? And again, main idea for today. All right, number 10, predict what would happen to the volume and internal pressure in experiment B of model 1 if a flexible container were used. So in experiment B, if we added heat, so if we took a balloon from like a cold condition and then we took it outside on a hot summer day, what do you think would happen to the balloon? It would increase in size. Okay, so what is that variable again? Size? Volume, right? So it's going to be the same deal. The volume would increase, the internal pressure would increase a little bit, but the walls would move out until they're equal again. Okay, now number 11, I know you guys didn't really understand this, but you got to understand this is very important for this whole assignment. Key idea. All right, talking about direct or inverse proportions. So again, what does that mean? A direct proportion is when one variable increases, it causes another variable also to increase. Or one variable decreases, it causes another variable to also decrease. Okay? An inverse proportion means if one variable goes up, the other goes down. Or one variable goes down, the other one goes up. So with an inverse proportion, they go in the opposite direction. So in experiment A, we added more gas and the internal pressure increased. So what would that be, a direct or inverse? That would be direct because we increased one and the other one went up. Algebraic expression, all I want for this, don't worry about this proportionality constant. But all we want to do for that, you can write this in. But N for amount of gas, and I'm going to do this proportional thing. And then pressure with a little I for internal pressure. What about on experiment B? We increased the temperature, and did the internal pressure go up or down? What was the relationship between the manipulated variable and the dependent variable? Experiment B, if we increase the temperature and the internal pressure went up, would that be direct or inverse proportion, you guys think? What is it? Experiment B, direct or inverse proportion. We increased the temperature and the internal pressure also went up. So is that direct or inverse? Did you say direct? Direct. So I'm going to do the same thing that I did over there. I'm going to put T this time. And so I know now, looking at these relationships, if the amount of gas goes up in a non-flexible container, the pressure is going to go up internal. So remember, this is talking about non-flexible container. If I increase the temperature of the gas inside the non-flexible container, the internal pressure will also increase.